Okay, next we have Lyman Page telling us about measuring the CMB from Chile.
Great, thanks. Hello. Like others, let me thank the organizers for a wonderful workshop. And like the talk we just heard, this is going to be much different than the talks from the previous couple of days. This is going to be technical. And what I want to do is tell you about what's happening in Chile and what we can expect in the future. Let me get started here. Let me give you an introduction. This, if it goes, there we go. This is a movie. I should say that I'm going to talk about a few experiments, ACT and the Simons Observatory. I'll talk about a few others. For ACT, Suzanne Staggs is the PI and Mark Devlin's the co-director. For the Simons Observatory, the spokespeople are Mark, Adrian Lee, and Suzanne, and Brian Keating is the director. That's the ACT telescope, and it'll switch to more interesting, just going to have to suffer through seeing the ACT telescope for a minute here. It'll switch to a more interesting perspective. And this is at our site of 5,200 meters in northern Chile. And I'll stop this in a second. And what you'll see is what you will see here is the whole neighborhood. It'll, one thing good, there we go. So let me stop it there. And this is the class experiment run out of Johns Hopkins. ALMA is down there. The Chajnan Tor is up over here, and those are names that'll come back in a minute. The polar bear array is off to the side right there. The Simons Observatory will go right in this region right there. Okay, so what is the status? The status is ACT's operating. We now have 11 seasons of data. We're taking data with this third generation of camera. Matt Hilton gave you a peek of the sorts of things we can do, and this version of ACT is called Advanced ACT. The polar bear / Simons array, and this was a collaboration between UCSD, well, many people in Japan and Berkeley, to name a few. They now have 3 telescopes, and the polar bear 2 receivers are coming online. I think the first one is down there, but those are their 3 telescopes. The ABS experiment, I'll refer to it, is done. That's history. And the class experiment has been taking data at 40 gigahertz since 2016 and recently installed a 90 gigahertz mountain receiver. And here's what's coming. Simons Observatory will, and I'll fill in some of this jargon for it. You'll see pictures of this jargon in a few minutes. We'll deploy a 6-meter large aperture telescope that follows a design by Mike Niemak, and it's ordered, right? It's being constructed, and something like 2021. The Simons Observatory will also deploy 3 to 4 small aperture telescopes dedicated for B-mode searches, primordial B-mode searches. CCAT Prime will go on that nearby mountain, 400 meters higher, above the water vapor, giving it an opportunity to look at higher frequencies better than we can at the ACT site. That also follows the NEMAC design. CLASS will finish deploying its suite of receivers to cover from 40 to up to 220 gigahertz. And the polar bear and Simons array should finish deploying 2 more receivers. So in roughly, let's say, 3 or 4 years, there'll be 3 6-meter telescopes, 3 2.5-meter telescopes, and 7 half-meter telescopes in this area. And they'll have various sensitivities, of course, and sensitivity to different things, but it's going to be it's already a very active place, and it will become more so soon. So the Simons Observatory. It is, we expect the first light somewhere near 2021, and there it is. The total between both sets of receivers is about 60,000 detectors. And let me introduce, so this is the NEMAC design. It's a cross-dragon. It can take a cryostat that holds 19 optics tubes. And we saw just a beautiful example of of an optics tube. It's very much like the bicep design there, except it's different because we do different things. But that is one optics tube. And the optics tube has, to keep in mind, has something like 5,000 detectors. So these cryostats are huge, right? And this one is not the biggest we could put in there, but it's close to, and we'll have 13 optics tubes. And there's only enough money to make 7 of them. So I'll have place for more, but 7 will be populated. And so everything I show you from these predictions will be based on those 7 optics tubes. And simultaneously, there'll be these 3, we'll see 3 or 4, probably 3, small aperture telescopes, and they're much smaller. They're much more like the bicep Keck design. Let me briefly show you, this is a slide from Mike Niemak. So this is, again, you can see it's the same design. It's going on the top of the nearby mountain, because it's going up there so it can look at much higher frequencies. It's much tighter constraints, so it's easier to build the Simons Observatory one first. And you can see they're going to have channels all the way down to microwave frequencies because Mike Niemak is a CMB person. But this is their first version of their first cryostat. So they hope to start sometime around in 2021. CLASS, which is the one out of Johns Hopkins, has been taking data, and they will end up with 4 telescopes spanning this range. So they just deployed one of those, and the second one is to be deployed sometime in the year, and they're just building them up. And so that is also there. So I want to sort of divide. I'm going to try to divide this in 2 parts, but talk about detectors for both of them throughout. So hopefully this is all clear. So large angular scales, of course, the goals are primordial gravitational waves and optical depth. In Chile, the atmospheric fluctuations are considerable. So you need to modulate the polarization to get above the atmospheric 1/F noise. And I'll show you an example in a minute. It's huge. And this is much less of an issue for South Pole. The atmosphere is just quieter there. So we showed, so all these experiments aimed at large angular scales have some kind of modulator in them. And so to be more specific, even if you're targeting large angular scales from Chile, we have yet to make a temperature map of the sky. No problems making a polarization map, but it's really difficult to make a temperature map. And you'll see how the modulator helps. So in Kusaka et al., we showed that the rapidly spinning half-wave plate is pretty effective. That was a warm one. The polar bear Simons array group. Simons array is different from Simons Observatory, by the way. Simons array group, it will also use a spinning cryogenic half-wave plate, which was built in collaboration with the Lightbird team. And they've been an ambient temperature version they've been working on. CLASS uses a different scheme. They use a variable polarizing modulator, which is just, it's a reflecting plane and then a wire grid that goes in and out. And the neat thing about that is it modulates instead of Q and U, as the half-wave plate does spinning around, between Q and V. So this is going to be one of the first dedicated experiments to measure the circular polarization. And Simons Observatory, we will be using one of these. And in addition, and we've had a number of side conversations here, a spinning half-wave plate, not only does it reduce the atmospheric fluctuations, as I hope to show you in a minute, but it also is great for beam systematics. The way to view it is because every beam is elliptical at some point. And what a half-wave plate does, if you spin it rapidly, it effectively rotates the polarization around inside that elliptical beam. What it also means is you only need one detector. There's no such thing as pair differencing. And we don't pair difference anyway, but this is another level of not pair differencing, if you will. Okay, so here's what the atmosphere looks like. Strong, 1 over F. Here's what it looks like in real time in Chile. So you can see this is a typical day. It might, over an hour, change by half a Kelvin, right? It's a lot. You modulate it, there's Q, you get that, blow it up, and it's white, pretty white. White enough, so the 1 over F, we can put the 1 over F down near millihertz, which means the data are stable on time scales of 500 to 1,000 seconds. That means you can stare at the sky for that long and measure a single polarization. That's not what we do, but in principle, you can do that. The other great, so that's one of the things you have to deal with in Chile. What Chile allows is a lot of sky coverage, and in a good clean patch. And this is huge. This is great for B modes. The SO strategy is going to be to cover 4,000 square degrees, so F a tenth of the sky. And when you do this, you do not need to delens to get to R of 0.002. So you can add delensing later and go deeper, but you do not have to delens. Okay? You have to take the foregrounds out, but you don't have to delens. There are more low emission regions available from Chile than from the South Pole. CLASS is making a very, I'd say, ambitious attempt. They're going to cover 75% of the sky, and their models show them that not only will they go after, they can recover a measured primordial beam, put limits on R, but they think they can get a good, or they're pretty confident they're going to get a good measurement of tau. So we'll see what happens. So what does the sky look like in Chile? Here's everything in green is accessible from Chile. These are various regions. That part is accessible from the South Pole. I'll show you in a minute. Bicep Keck, which we just heard about, is looking right in there. Here, just to show you, is a movie of what that means. So this is the coverage that we have with ACT right now. This is the Planck map, we're just using it, but this is as much of the sky as we've covered already. Okay, so you can see these are the data we're analyzing. That's covered with a 1.5 arc minute resolution. So going back to that map, focusing now on large angular scales, this is where Spider recently looked there. There's the bicep patch, and you can see these are these contours showing various levels of cleanliness. Just to pick a few points, there's T, I've forgotten what these stood for, T, M, and B. So green, middling, greenish, okay? You can see what those levels mean. Here's let's go now to I haven't included your most recent result here. But here, these are in the last few years, all the data for TT, EE, and BB. These are, for those who don't see these every day, these are the RMS fluctuation levels. And this is Bicep Keck, who remain, and I think, and will remain for the next few years, the ahead in this search for the primordial B modes. So what do those three regions look like? Those are the levels. So this is zoomed in on the largest angular scales here, so those are the levels. So it's clear we're just all going to be measuring foregrounds, and the question is, how well can you measure them? Okay, so here's my take. Jacques had his list. We view this measurement challenge similarly. But there are some differences. At least, I think to be convincing, you're going to need independent detections with independent instruments at something like the 5 sigma level to convince a particle physicist that you've measured primordial B modes. And I think ATLAS and CMS are a great example, right? There were claiming detections of something at a 3 sigma level, both. Until they got together and until they took more data and did more analysis and showed that wasn't right. I've forgotten what it was they were claiming to see, some new resonances. Anyway, measurements of multiple regions of the sky, critical and an unambiguous frequency spectrum. And the large aperture telescopes will be really helpful for cleaning at fine angular, a half-degree angular resolution at 30 gigahertz. So just to get a half-degree angular resolution at 30 gigahertz requires at least 1.5 meters. Just a step back, or just a picture of the evolution and technology over the years. These are about the same size. That was the first detector to measure the anisotropy with a bolometer. And this is a modern array. This is from NIST builds the arrays for ACT. This is one of the advanced ACT arrays. This has 500 feeds. We have 3 of these observing right now, and the combination is per second 3 times more sensitive than Planck. Okay, just to give you a sense. And so they are really, they're sensitive. This is advanced ACT wafer PA4, and just to give you a sense for how this works, because it's different than what we just saw with BISAT. Just before showing you this, these are pictures taken at NIST. NIST has been just amazing in what they're producing, just absolutely fabulous. So, and here's the idea. These two, so this is at the bottom of, you funnel down the radiation with some feed horn, and then it picks it up. You pick up 2 orthogonal polarizations with these probes, and you say, why do they have that funny shape? And that's so you get a large bandwidth and all that stuff. And then they peel off, and then they split into 230 gigahertz and 150 gigahertz for each probe, right? So each one of these then has 4 detectors, okay? So there are 500, roughly 500 feed horns that go to this, and about 2,000 detectors. And there it is, about 15 centimeters across. Just absolutely marvels of technology. Just beautiful work in detector physics. For small angular scales, we've seen a lot of these lists. I just want to highlight one just to tweak Francois a little bit. I don't think Planck is out of the woods on H0, mostly because I think in all experiments there are residual systematics, and I would say in that, and I should say Dick, I can tweak him too, right? There's still A sub lensing, which is off by, from the 2-point function, which is off by a little, between 2 and 3 sigma, and when you marginalize over it, H0 moves up half a sigma. Moves up 1 sigma. And the neutrino bounds move up 1 sigma. So it's important to get these things right and to follow up. And these small angular scale experiments. Pardon me? No, I said one of your sigma. So it could be 68, or 69, or 70. Good. Yeah. No, I agree with that. Yeah. Okay. So what do we observe here? So where are we going to observe? So this is again about going back to the Simons Observatory. Again, this is the coverage. Numbers. We heard these sort of satellite proposals from Shaul. They're a little less than 1 microkelvin arc minute. We should, and I'll show you how we get this number, we should be able to reach about 2 microkelvin arc minute, but over that 4,000 square degrees with the large telescope, with the large angular scale telescopes. And for the small angular scale telescopes, our goal is to get to about 6 microkelvin arc minute with 1.4 arc minute resolution. And another great thing you can do with Chile is we heard about all these surveys, is we just about completely, I think we do, completely overlap with DES. Completely. With LSST. Completely. Parts of DAISY. There's already been a lot of work with HSC, KIDS, and some actually Matt was working on cross-correlating with gamma. These are all in the works. They're all going on right now. Okay. Science forecast matrix. So this is Simons Observatory, S4, class, Lightbird, Pico. You can see here's what exists. So here's 1 sigma for bicep Keck. we think we can get to these limits, and these include foreground models and all that sort of thing. And so these are the sort of levels that are being talked about all the way through here. You can see sigma, these are sigma event effective compared to what we have today. So there'll be improvements across the board. Sigma on the mass of neutrinos. Anyway, those are the numbers. I want to just talk a bit about the sensitivity for the large aperture telescope, so for the one that gets to fine, the fine angular scale one. So I'm just picking on 90 and 150, but of course these all have other channels to clean out foregrounds. And I'm going to use the ACT numbers because I think because there's some of the most sensitive detectors around, but they're not, we just saw, they're not that similar from SPT or bicep Keck. So you can sort of slot in any one of these. Right now, and right now this is where we are at these two frequencies. The way to read this is, say at 150, it's 18 microkelvin, and that means efficiency times rho times time in year. Okay? So if you had 5 years and 20% efficiency, you would get 18 microkelvin per square arc minute over 40% of the sky. That's what SO will bet, and that's based on this with a more sophisticated model from Matthew Hasselfield. S4. The S4 model is completely based on the SO model. All it did was it takes, instead of 7 optics tubes, you have 19. Instead of 1 telescope, you have 2. Instead of 5,000 detectors per optics tube, you have 6,000. That's the only difference. It's directly scaled from SO by the same people. And so all that gets you a factor of 3. So a factor of 2 to 3 improvement there, and another factor of 3 improvement there. So that's and this is, I think, the way to view the sensitivity because it cancels out all the different assumptions on observing time. And let me just end here with just another element of this whole business, and that is estimates of the ultimate limits. And again, these are estimates. So what has been achieved? So this is not per arc minute, this is going back to per detector. So these sort of levels now have been achieved for a single detector. These are microkelvin arc seconds sensitivity. Pardon me? Absolutely. All these are on the ground and at a high site. So this is, bicep, SPT, ACT. Definitely, absolutely. This is all on the ground in Chile, right? So this is, and so you can estimate what's possible. And of course you have the CMB loading, you're going to have 10 Kelvin of atmosphere loading, and then you have loading from your instrument, and you can imagine how well you can possibly do. And again, these are estimates. I mean, these are crude, right? They might be proposal worthy, but probably not even that, right? So you can get some sort of best possible estimate. And this is actually John Goodmanson and I did it completely different ways and he did it much better than I did, came up with similar numbers. The point isn't the absolute number, but the point is that you can improve. There are gains to be had in the sensitivity. And if you improve the detector sensitivity by 15%, to get to the same science result takes 30% less detectors, 30% fewer detectors. That's huge. When you are building thousands and hundreds of thousands of them, that's millions of dollars. So there is a huge benefit to improving the detector sensitivity and the receiver sensitivity. But ultimately, we would just be limited by foreground emission plus. So it's not going to be this. We'll ultimately be limited by foreground emission plus low-level systematics. So let me end there. And of course, say what we all in this field know, there's just a ton more exciting science in the CMB. There's a ton more to do in instrumentation. And there should be a ton more workshops at the ICTS to talk about it. So let me stop there. Thank you.
Okay, questions for Lyman?
Lyman, what is the reason that two practically identical telescopes will be staying on in Chile.
In Chile?
6 meter, yes.
Yeah,
Or in reality 3.
Yeah, so there'll be ACT there, and there'll be the Simons Observatory, and then up on that higher peak, that 400 meters, that is, okay. The higher, the Chajnan Turwan CCAP Prime and Simons Observatory are the same design. And the reason they're the same design is because Mike came up with that design, and all the engineering was done, and we could just slide in and use it. So that's the only reason, so those are two. The other three are just already there, the smaller ones, the 2.5 meter.
Is it possible to use these 3 telescopes for interferometry or?
You're ahead of us, yeah. But we've got this, and right down the road is this amazing interferometer that's built to be an interferometer. So it's almost not too far away. So I think they'll.
Okay. Zish? Yeah, I thought, Lyman, do you want to comment on the need, the status of ground-based observatories in the Northern Hemisphere?
Yeah, the potential is great, because this is, they're much less well developed. It's been a while, because there's a lot of nice clean sky up here you can look at. So if you can get things together, there's Chow Lin and colleagues are taking, you probably know more, right, to a bicep style receiver to Tibet, right? And there are possible plans for northern India. There's a ton to be done from the ground still, and there are other great sites. This is just, the reason we went to Chile. We were thinking of going to Hawaii. We went to Chile because I had a postdoc who was Tony Reedhead's student, and Tony was thinking of going to Chile back for CBI, and told us about it. And we said, oh, that looks good. So that's how this all got started in Chile.
If you were to say so, how would you prioritize the science in terms of polarization, high L, or clusters? What should be the most high priority science?
Everything.
No, prioritize.
Yeah, right. It's all great. I mean, we don't know if we're going to run into some limit for foreground, for really something really difficult for foregrounds. I would guess, just naively, the limit on B modes is going to be about 10 to the minus 3. And the only reason this gives you a sense for the depth of that guess. Just generally, at least in every experiment I've done, if you're measuring something and there's junk in it, you can usually model the junk about a factor of 10 and sort of believe it. You can subtract. I'll not try to be vulgar here as I would be if it weren't an audience, right? You can subtract stuff and get a factor of 10 below your noise, typically. And we know the noise from bicep is at R of 0.1. R of 10 to the minus 3 is 100 times an R, but in the map it's only a factor of 10. So when we talk about improving the limits from, say, where bicep is right now, 0.07 down to just 0.007, as class is doing, that's a factor of just 3 improvement in the map. Right, so that's what that number comes from. And then it's not that you can't do better, it's just that doing better gets really, really hard. Michel might disagree, because I know he's getting lower limits, but.
Rita?
All right, so I wanted to ask about the very end. You mentioned that if the detector performances were to improve by some percent, we wouldn't have to make as many number of detectors.
Right.
So is this a comment that no one gets to photon noise limited, or?
Yeah, we're not quite there, that's all.
Okay.
And there's more to be done.
Okay, but if we were at 410 Kelvin atmosphere there, that's.
You stop there, right, absolutely. No, that's just, now it's like 30% of the noise, or 40%, something like that for us. I've forgotten the exact number. But it's, yeah, no, I mean, this is building a better receiver. It's a really worthwhile thing to do. The gains are huge.
Any final questions for Lyman? Okay, if not, let's thank him.
Thank you.
So we go to a coffee break now and come back at 3:25.